Hi, thank you for joining me for our poster presentation today, which is particle characterization and identification with Hound. The three people here worked on this poster: Donna Chen, Lisa Kraft, and myself. This poster is about analyzing particles in different types of forms. And so particles come in many different stages of biologics drug development. Sometimes they are wanted and expected, and sometimes they are unwanted. So we're going to talk about ways to characterize both. When considering a particle analysis method, you need to think about the function. What's going to count and size particles in the way that you need? It's going to provide morphology information. Is it going to provide orthogonal information for a definite identification? The throughput of the device, does it match the needs of the laboratory? And ease of use, which is, can you just walk up and use it? Or is it specially trained operators who need to be the only ones who use the instrument? Our goal when we developed Hound was to make sure that anyone can walk up and use the instrument. So it does count size and shape. If you need just that information, it does that automatically. If you also need identification, you have 3 lasers built in that can do identification by Raman or laser-induced breakdown spectroscopy, or LIBS. Counting is automatic. You put in your sample, you select the area that you want to image and count. Hound will go through, raster through the sample area, image every spot, stitch the image together, count the particles, report the information about where their coordinates are and what the morphology of the particle is. It can pick up as particles as small as 2 microns and accurately measure particles as large as 15 millimeters. You have a lot of flexibility in how you put a sample on Hound. In this particular example, we're going to use a filter round, which can filter a sample if it's aqueous. You can also disperse a powder across that surface. If you just see a single particle in a solution, you can just pluck that particle out and put it on that filter round as well. If you want to avoid capturing smaller particles that may not be visible, you can pick a different pore size and filter those out. Let's use an inhaler as an example. During drug development, you probably determine what the proper particle size was for your API. How do you confirm after manufacturing and it's in a device that that particle is still that size? Or how do you confirm that your inhaler is not introducing particulates, solid particulates, when you actuate it? So what we're going to do is we're going to actuate our inhaler within this funnel. And the funnel is under this clamp is the actual filter round. And so we're going to actuate the inhaler twice, capture any particles either on the surface of the filter or on the funnel, rinse the funnel so any particle ends up in the filter round, take the filter round, move it to Hound. So with 2 meter dose inhalers, we get different particle counts. And so you can see from the distribution that most of those particles fall in a subvisible range. You can actually set controls on the Hound to determine what bin size you want to set if you're looking or focused on certain particle sizes. Hound will also give you the morphological information on your particles. The next example will talk about how that factors into simplifying the identification process. In this example, we'll use a nasal spray. The nasal spray, like most drugs, have other materials that are not just the active pharmaceutical ingredients. In this particular example, we're trying to determine how many API particles are present. The problem is that there's a lot of particles that are not API, and so we need to differentiate those. So let's start with the sizing information. The API is about 4.2 microns in spherical. Cellulose, which is one of the fillers, is about 37 microns. These overlap, and the difference really is the elongation factor, where the API particle is spherical, the cellulose is not. So if we were trying to identify small particles or particles under a certain size, we can use the elongation factor so that we have a smaller sample set to analyze and focus on things that are less likely to be the filler material. When we did a particle count of the sample, it was about 45,000 particles. By leveraging the elongation factor and the morphology information, we could tailor the Raman identification to a smaller subset that was more practical to do in an experiment. So 3,000 particles can get identified by Raman in about 3.5 to 4 hours, and from that we can get the API size distribution and understand the percentage of API that's present in the sample. The Raman applications are great for organic and inorganic materials and distinguishing those. LIBS is the best at determining metals and elemental analysis. So what we're going to do in this case is talk about what happens when we have a metal contaminant that shows up in a sample. When a contaminant shows up, the first question is what is it? And the second question is where did it come from? A standard piece of aluminum has a certain spectra, so you could identify any aluminum material that would match to that reference. But all materials have a slight difference depending on how it was manufactured or what other materials might be on the coating. And so we see this example with this crimp cap that has an extra peak at about 403 nanometers. And so if this was a contaminant, you could quickly identify not just that it was aluminum, but it came from a certain material. So this works for Raman and for libs, which is you can create a reference library or retain references for things that you are using as part of your normal process. So this database is expandable. You can add your own part. It starts with about 200 reference spectra. You can add your own based on what is most relevant to you. So whether that's an API particle or a different polymorph or contaminant options, it's about 15 minutes to add a sample directly to the database. And then it's there specific to your lab and specific to your application for whenever you need it again. I hope in this brief talk I've given you some idea about how Hound can be used in a complement of different applications where you need particle analysis and identification. If you have further questions, please feel free to contact us at info@onchainlabs.com. Thank you.